Okay, so here we are. We finally arrived at the last lecture on fine-tuning of the Higgs boson. I think by now you can definitely see why this is not covered in elementary discussions of fine-tuning, but I hope it was worth the journey because I think we covered a lot of fundamental things about the universe. Okay, so now we know something about the Higgs boson, but the question becomes, okay, where is the fine-tuning? And the fine-tuning of the Higgs boson is a problem about its mass. Its mass is very finely tuned. That's where the fine-tuning is. Remember we said that the Higgs boson is what gives these particles, like the electron, like the W particle and the Z particle, like the quarks, their masses. And it is interacting with the Higgs field that gives these particles their masses. The Higgs boson is just a manifestation of the Higgs field, and we keep switching back and forth. So for simplicity, we're just going to say that these particles interact with the Higgs boson. And the way they actually get their mass is there's something known as the Higgs expectation value. And that gets multiplied by a coupling constant known as the Yukawa parameter. And so imagine taking the Higgs mass. This is just a slightly inaccurate analogy, but imagine taking the mass of the Higgs boson and multiplying it by the Yukawa parameter. And each particle has its own Yukawa parameter. So light particles like the electron would have a small Yukawa parameter. Heavy particles like the W and Z particles would have a large Yukawa parameter. And for a given Yukawa parameter, if the Higgs boson were very heavy, then when you did that multiplication, the electron would be heavier, and the W particle would be heavier, the Z particle would be heavier, etc. So we can think of the notion that the Higgs boson, its mass, regulates the masses of the other particles. And we've already talked at some length in our previous videos about how critical the mass of these elementary particles is to life in the universe. They are very finely tuned. Those masses are very finely tuned, and we've already covered that ground. And so this means then that the mass of the Higgs boson also has to be very close to what it actually is. And when we say what it actually is, how do we figure something like that out? Well, when the Peter Higgs and others hypothesized the existence of the Higgs field and the Higgs boson, from the known masses of the W and Z particles, the electron and so on, and from the interaction terms between the Higgs field and the fields for these particles, those are the terms in the Lagrangian, one could back calculate what the expected mass of the Higgs particle is based on the observed values of these other masses and based on the parameters in the standard model. And that calculation suggested a particle somewhere between 120 and 150 GeV, giga electron volts. So that's about 120 to 150 times as heavy as the proton. Pretty heavy. So that was what would have been expected, and that was what the Large Hadron Collider started looking for. And in fact, when the Higgs boson was found, it ended up weighing about 125 GeV, and scientists have been working to get that, narrow that mass down more and more accurately. And so here's an article, you can see its citation here, that the mass of the Higgs boson has been now measured to a precision of 0.1%, and that newest value is 125.35 GeV. Okay, so then where's the problem? Where's the fine-tuning? Because theoretically we expected to find a particle between 120 and 150 GeV. Scientists find a particle that weighs 125 GeV. Everything seems hunky-dory. Well, not so fast, because the mass of the Higgs particle can also be thought of or calculated from first principles according to the Standard Model as something known as the sum of the bare mass and the quantum corrections or quantum fluctuations that add to the Higgs mass. So when you don't calculate it based on how it reflects in the other particles, but just calculate it from what is known about the Standard Model itself, get a very, very different answer than 125 GeV. Now, we can't see the bare mass and we can't see the quantum fluctuations. We know that their sum is what gives us 125. But we can't measure them, but we can make theoretical calculations about them in a reasonably accurate way if the Standard Model is correct. Okay, so let me just go ahead and read with you this quote from the wonderful book, A Fortunate Universe by Lewis and Barnes. So, the mass of the Higgs boson presents us with a conundrum. Our quantum mechanical calculations predict that it should have a mass of 10 to the 18th GeV. That's a billion giga-electron volts. Life requires a value not too much different from what we observe, so that the masses, and what we observe, remember, is about 125, but on the order of 100 giga-electron volts, so that the masses of the fundamental particles are not disastrously large. There must be an as yet unknown mechanism that slices off contributions from the quantum vacuum, reducing it down to the observed value. This slicing has to be done precisely, not too much and not so little as to destabilize the rest of particle physics. This is a cut as fine as 1 part in 10 to the 16th. Maybe there's a natural solution to this cutting, but it seems quite lucky for our universe that the slicing resulted in stable particle physics. This problem, known as the hierarchy problem, keeps particle physicists awake at night. And here again, from Quantum Magazine, a blurb about the hierarchy problem. The Higgs boson gives mass to other elementary particles. They in turn influence the mass of the Higgs. Extremely massive particles at the Planck scale, we won't worry about that now, a high energy scale associated with quantum gravity, should inflate the Higgs mass and with it the mass of everything else. This is the blurb about how the calculated mass would be 10 to the 18th, and if it were that big, the mass of all the other particles would also be that big, yet they do not. So the Higgs mass is 100 million billion times lower than the Planck scale, which is where the mass would have been expected to be. And so again, another quote from Barnes and Durant. So we suspect that we're missing something, a physical effect that wipes out the additional mass added from quantum fluctuations and does so very precisely. Wiping out a factor of 2 is not going to save the day, as the predicted Higgs mass would still be immensely larger than is measured. A factor of 100 or 1,000 doesn't help, nor a billion, nor a trillion. And I don't mean that we make it a trillion less, we mean we divide by a trillion. So we need to balance the contributions from the vacuum by a factor of 10 to the 16th. That is how fine the cancellations between the bare mass and the quantum corrections has to be. It is an incredible amount of fine-tuning, and the entire stability of particle physics and obviously then of chemistry and of life depends on this fine-tuning. So from a Wikipedia article, more technically, the question is why the Higgs boson is so much lighter than the Planck mass. One would expect that the large quantum contributions to the square of the Higgs boson mass would inevitably make the mass huge. Again, a lot of jargon, but you're getting the point. Comparable to the scale at which new physics appears, unless there is an incredible fine-tuning cancellation between the quadratic radiative corrections and the bare mass. So these are the quantum corrections. This is the bare mass. Remember, we can't measure either of these. We just see their sum, and they have to be incredibly balanced, and there's no particular reason that they should be so well balanced as to reduce the Higgs boson mass to what we observe. And again, from another physics website, In the Standard Model, the predicted experimentally measured value of the Higgs mass is calculated as the sum of the bare Higgs mass parameter, one of the fundamental parameters of the Standard Model, and so-called quantum corrections that capture the effect of the Higgs interactions with itself and other particles. Recovering the measured value of the Higgs mass requires an unusually delicate cancellation between the bare Higgs mass and its quantum corrections. And there is no physical reason that we know of that this cancellation had to occur. And so here the quote continues to make that point. If we imagine selecting a set of values for the fundamental bare parameters randomly from the set of all possible values for these parameters, it is highly unlikely that the chosen parameters will exhibit the required cancellations. Only an improbable, and again improbable to 1 part in on the order of 100 million billion improbable, only an improbable fine-tuned set of parameter values will work. The larger the cutoff, the more the fine-tuning is needed. And so now you see the fine-tuning that is involved. We don't know why it happens, as Barnes and Geron said, where we feel very fortunate, of course, that it happens. And all of life in the universe depends on this. If you do not believe in intelligent design, this incredibly lucky accident. And if you do believe in intelligent design, it is the product of the majestic design and the finesse with which God has designed this universe. And that, of course, is our point of view. And so I hope that this long journey has been worth it for you to understand a little bit about the fine-tuning of the Higgs boson. Thank you, take care, and God bless.